Hi everyone, welcome back to array series. So today we are going to see a different problem which says you are given an array of size n and you have to return the equilibrium index in that array and return -1 if no such index exists. So first of all, let's see what equilibrium index actually is. So here is the definition of equilibrium index. So it is an index such that the sum of elements till that index and sum of elements after that index is same. So if you see this example, then the sum of these elements is 2 plus 4 6, 6 plus 1 is 7, 7 plus 10 is 17, and some of these elements also is 6 5 6, which is 11, 11 plus 6 is 17, right? So if you see sum of elements till this index and sum of elements till after that index is same. So if you see index number 4, so sum of elements till index 4 is 17 and sum of elements beyond that index is also 17. So what you can say that index 4 is your equilibrium index. So if we have to find for all the arrays that would be given to us, we have to check if there any index, if there any such index exists, and if it doesn't exist, we have to return -1. So what we are going to do is we will be we will start solving this problem from the brute approach, and then we will be proceeding with the better approaches. Along with that, we will be seeing codes and also the time complexity and the space complexity of those approaches. Alright, so let's first start from the very basic approach. So let's again write down the example here. So you have 2 4 1 7 3 3 6 5 and 6. So what we are going to do in this approach is I will see for every index, I will see if that index is my equilibrium index or not. Okay, so what I'm going to do is, let's index them all. So what I'm going to do is, for this index, for 0th index, I will check if this is an equilibrium index or not. So what I'll do is I will check the sum of the elements after that index and sum of the elements till that index is same or not. If it is same, I will return that index and end my loop there only. Otherwise, I will check for the next index. Then I will check for this index. I will check if this might be my equilibrium index or not. Then I will check for this, if this might be my equilibrium index or not. Then again, if this can be my equilibrium index or not. So what I'm going to do is I will run a loop to check the sum till this element, and I will again run a loop to check the sum of the elements till after that index. So what we are going to do is, for every index we will just check if this could be equilibrium index or not. All right, so let's see the code of it. I've already written the code. So we are taking two arguments here, array and the size of the array. So what I'm going to do, I will run a complete loop over the complete array, and then I have taken two variables, left sum and right sum, to know that what is the sum of the elements, till that index, and what is the sum of the elements after that index. So what I have taken, as we discussed that we will be checking every time. We will consider that we will try that we will check if this index is my equilibrium index or not. So what I'm going to do, what I'm doing here is I am checking if this is my array, and if this is the index for which I am checking if it is my equilibrium index or not. I am taking the sum. I am running a loop to take the sum till that element, and I am running a loop to know the sum of the elements beyond that index. So I have run my loop from 0 to till that element to take the left sum, which will have the sum of the elements on the left side till that element and till that index, and then again I have run a loop after that index till my size of the array, and I have captured that in my right sum. And then at the end I'm checking if my left sum is equals to right sum, and if it is, then I'm just returning I, otherwise I'm returning -1. Okay, so I hope means this is very simple, very simple approach. So let's see the time complexity and space complexity. So here I'm running my loop for n time, and if you see, for every index, once I'm checking the right side and once I'm checking the left side. So more or less like if in worst case, how much will I go? I will go for n size. I will iterate over the complete array, right? So if you see, for every n time, what I'm checking at least n times. Then again I'm checking. Oh no. So every n time, what I'm doing is, for every index, what I'm checking, at least I'm checking for n time, n up to n times. So what is the time complexity? Time complexity is order n square, right? Why n square? See, if you are at index 0, you will check up till you will check n minus 1 elements. If you are at index 1, you will check n minus 2 elements till that element, and then you will check two elements for 0 and 1. Similarly, for 2, you will check 3 elements to the in the left side, and you will check n minus 3 elements in the right side. So more or less, you are checking n elements every time, right? You are checking n elements every time. So every time you are checking n times. So n times n is n square. So that's the time complexity of this approach is n square. Space complexity is order 1. We have not taken any extra space, right? I hope this approach is clear to you. Let's come to second approach. Let's write this example again. So it is 2, 4, 1, 7, 3 and 6, 5, 6. Okay. 2, 4, 1, 7, 3, 6, 5, 6, 0, 1, 2, 3, 4, 5, 6 and 7. So what I'm going to do in this approach is, I'm going to take two separate arrays. One will store, one I will name as left array, and one I will name as the right array. So what it is going to do is, it will store the sum of the elements in the left side till that index. So what it will do, for this it will store 2, for this it will store 6, like sum of the elements, sum of the left side elements till that index, right? So here it would be 7, here it would be 14, for this it would be 17, for this it would be 17 plus 6 is 23, then it would be 28, and then it would be 34, right? For right side, same, we will be storing the sum of the elements of the right side till that index. So it would be 6, it would be 11, 17, then it would be 20, 27, 28, 32 and 34, right? Now I have my left side array, I have my right side array. What I'm going to do is, I will check if the array at left at I is double equals to right at I, right? Right of I plus 1, right? What I'm going to do, if I'm going to check if this is equal, 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 yes, this one is equal, that means this one is my equilibrium index. As simple as that, right? Let's see the code of it. So I have taken two arguments, array and n. I have taken two arrays to store the sum, which I have initialized with 0 as of now. Then in left of 0, I have stored the sum. I've stored the 0th index value, and then here I have stored the array at n minus 1. Then what I'm going to do is, for I is equals to 1, I is less than n, I'm storing the sum here, right? So what is the approach that I'm adding? Left at I minus 1 is plus array at I. Similarly, I'm doing it for right side elements, and then here I'm checking. Once I've run my loop, I'm checking if left at I is double is equals to right at I plus 1, and if it is equal, I'm just returning I, otherwise I'm returning I minus 1. So let's see the time complexity of this. So time complexity is order n here. Okay, now if you see, this also you are running for order n times, and here also you are running for order n times, right? So what is the time complexity? So time complexity is order n plus order n plus order n, which is order 3n, which is order n, right? Time complexity is order n. Now if you see space complexity, I have initialized two arrays of size n, right? So space complexity is order n. So if you see, in approach 1, we had time complexity of order n square and space complexity of order 1. But in approach 2, we have decreased the time complexity by order n, and we have, means like we came to, till order n, and then space complexities are also order n. Now let's see in third approach how we are going to remove this extra space as well, and how we are going to solve the same problem in order n time but without any extra space. Again, let's write the example. So it is 2 4 1 7 3 6 5 6, right? 2 4 1 7 3 6 5 6, right? So it is 0 1 2 3 4 5 6 7. So what I'm going to do is I'm going to keep a variable. Let's name it as right. And what I'm going to do is I'm going to run a loop and take the sum of all the elements. So if you see, what is the sum of all the elements? It is 6, 6 plus 6, 7, 7 plus 7, 14, 14 plus 3, 17, 17 plus 6 is 23, and it is 34. Yeah, it is 34. We have seen in previous example also that it is 34. So what I'm going to do is, in one loop I have taken the sum of the elements. In the second loop, what I'm going to do is I'm going to take one more variable, name it as left, and I'm going to add the value of that index in this variable left, and I'm going to decrease the value from right, and I'm going to see if those both are equal, and if both are equal, I've got my equilibrium index. So this approach is as simple as that. You don't need any extra space, and you just need one extra variable, and you solve this problem in order and time complexity and order one space complexity. Let's do a dry run for this. So I'm going to initialize my left is equals to 0 and right is equals to 0. I will run one loop and initialize my right with 34. And I'm going to do in my second loop, I'm going to start from the very beginning, and I'm going to add this value in left and decrease this from right. Then again I'm going to add this value in my left and decrease this from right. It would become, say, 26. Then I'm going to add this value in this, and I'm going to decrease this value from here. Then I'm going to add this value here, decrease this from here. So 25 minus 7 is what? It is, have I done any mistake? So it is 7 plus 7, 14, and here it is 34, 33, 34, then it came here, then it came 26, and then 25. 25 minus 7 is 18. 18, yeah, 18, but then it is right. No, sorry, I think I've done one mistake here. Let's run it again. So I'm adding this to here. This is 34, so I'm making it 32. Then this becomes 6, and this becomes 28. Then this becomes 7, and this becomes 27, right? Then this becomes 14, and this becomes 20, right? We have done this also. Then I add this to 14, 17, and then I decrease 3 from 20, so it becomes 17 and 17. Now both are equal. Then I know, because right side only contains this side sum and left contains this side sum, so I can say this index is my equilibrium index. As simple as that. Let's see the code of it. So I have taken two variables, left and right. I am running one loop, and I have taken the sum of all the elements and captured it in right variable. Then I have again ran a loop. I am taking the sum of the elements of the left side. In here I am adding the sum, here I am adding the value, and here I am decreasing the value. Okay, decreasing the value. Okay, so here I am adding the value, and here I am decreasing the value, and at the end I'll check if left is equals to right, and if it is equal, then I'm just returning I, otherwise I'm returning -1. Now let's see the time complexity and space complexity. So here if you see, time complexity is what? Time complexity is order n of this loop. Then here time complexity is again order n. I'm running this for order n. So if you see, time complexity is what? Order n plus order n, which is order 2n, which is equal to order n, right? Time complexity is order n. But if you see, I have not taken any extra space. So what it is? Says space complexity order 1. So from n squared time complexity, we came to order n time complexity, but we increased the space complexity there. But at the end, we are able to solve the problem in order n time complexity order n and space complexity order 1. I hope it is clear to you. Thank you.